The basic question is, does life exist beyond Earth? Scientists who are called astrobiologists are trying to find that out right now. Most astrobiologists are trying to figure out if there's microbial life on Mars, or in the ocean under the frozen surface of Jupiter's moon Europa, or in the liquid hydrocarbon lakes that we've found on Saturn's moon Titan. But one group of astrobiologists works on SETI. SETI is the search for extraterrestrial intelligence. And SETI researchers are trying to detect some evidence that intelligent creatures elsewhere have used technology to build a transmitter of some sort. But how likely is it that they will manage to find a signal? There are certainly no guarantees when it comes to SETI, but something called the Drake equation, named after Frank Drake, can help us organize our thinking about what might be required for a successful detection. If you've dealt with equations before, then you probably expect that there will be a solution to the equation, a right answer. The Drake equation, however, is different because there are so many unknowns. It has no right answer. As we learn more about our universe and our place within it, some of the unknowns get better known, and we can estimate an answer a bit better. But there won't be a definite answer to the Drake equation until SETI succeeds, or something else proves that Earthlings are the only intelligent species in our portion of the cosmos. In the meantime, it is really useful to consider the unknowns. The Drake equation attempts to estimate the number of technological civilizations in the Milky Way galaxy, we call that N, with whom we could make contact. And it's usually written as N equals R star multiplied by F sub P multiplied by N sub E multiplied by F sub L multiplied by F sub I multiplied by F sub C, and lastly multiplied by capital L. All those factors multiplied together help to estimate the number of technological civilizations that we might be able to detect right now. R star is the rate at which stars have been born in the Milky Way galaxy over the last few billion years. So it's a number that is stars per year. Our galaxy is 10 billion years old, and early in its history, stars formed at a different rate. All of the F factors are fractions. Each one must be less than or equal to 1. F sub P is the fraction of stars that have planets. N sub E is the average number of habitable planets in any planetary system. F sub L is the fraction of planets on which life actually begins, and F sub I is the fraction of all those life forms that develop intelligence. F sub C is the fraction of intelligent life that develops a civilization that decides to use some sort of transmitting technology. And finally, L, the longevity factor. On average, how many years do those transmitters continue to operate? Astronomers are now almost able to tell us what the product of the first 3 terms is. We're now finding exoplanets almost everywhere. The fractions dealing with life and intelligence and technological civilizations are ones that many experts ponder, but nobody knows for sure. So far, we only know of one place in the universe where life exists, and that's right here on Earth. In the next couple of decades, as we explore Mars and Europa and Titan, the discovery of any kind of life there will mean that life will be abundant in the Milky Way. Because if life originated twice within this one solar system, it means it was easy, and given similar conditions elsewhere, life will happen. So the number 2 is a very important number here. Scientists, including SETI researchers, often tend to make very crude estimates and acknowledge that there are very large uncertainties in these estimates in order to make progress. We think we know that R star and N sub E are both numbers that are closer to 10 than, say, to 1. And all the F factors are less than 1. Some of them may be much less than 1. But of all these unknowns, the biggest unknown is L. So perhaps the most useful version of the Drake equation is simply to say that n is approximately equal to L. The information in this equation is very clear. Unless L is large, n will be small. But, you can also turn that around. If SETI succeeds in detecting a signal in the near future, after examining only a small portion of the stars in the Milky Way, then we learn that L, on average, must be large. Otherwise, we couldn't have succeeded so easily. A physicist named Philip Morrison summarized this by saying that SETI is the archaeology of the future. By this he meant that because the speed of light is finite, any signals detected from distant technologies will be telling us about their past by the time they reach us. But because L must be large for a successful detection, we also learn about our future, particularly that we can have a long future. We've developed technologies that can send signals into space and humans to the moon. But we've also developed technologies that can destroy the environment, that can wage war with weapons and biological terrorism. In the future, will our technology help stabilize our planet and our population, leading to a very long lifetime for us? Or will we destroy our world and its inhabitants after only a brief appearance on the cosmic stage? I encourage you to consider the unknowns in this equation. Why don't you make your own estimates for these unknowns and see what you come up with for n? Compare that with the estimates made by Frank Drake, Carl Sagan, other scientists, or your neighbors. Remember, there's no right answer. Not yet.
A spacecraft from another solar system invades the night sky. But this is not our sky. And we are the invaders. The search for alien life has begun.
We think that other worlds, perhaps other Earths, if you will, exist. We know of hundreds of other planetary systems right now, and that may be the tip of the iceberg.
It isn't conceivable, really, that there would not be life. Is it intelligent? I don't know. That's a whole other issue.
Within a few decades, unmanned probes equipped with artificial intelligence may find life on planets beyond our solar system.
2014, that's the magic year. That's the magic year where the terrestrial planet finder goes up into orbit, and its explicit mission is to find evidence of up to perhaps 500 Earth-like planets orbiting other star systems.
There is no reason not to think that on some of them, somewhere, you would find multicellular organisms like ourselves.
The life we have on Earth must have spontaneously generated itself. It must therefore be possible for life to be generated spontaneously elsewhere in the universe.
We now take a simulated journey, scientifically verified by leading experts, to a planet called Darwin 4. The life it supports tests the limits of technology and the intellects of the greatest minds of our generation. Because here on Darwin, life is truly full of surprises. An interstellar spacecraft named Von Braun leaves Earth orbit for a planet some 6.5 light years away. Are we ready to confront the technical challenges of a mission that will take decades to complete? To find out, a team of top scientists, engineers, and artists create a virtual mission to Darwin 4, fourth planet in a binary system called Darwin.
It seemed utterly important to me that the foundation to create a world was to make sure that the world was acceptable to the science community.
Then we put together a team of scientists to have a look at that concept and to make sure that the laws of physics and chemistry were all represented in that model.
Today, we search for planets like Earth through telescopes. The Darwin 4 mission simulates the next giant step, the unmanned quest to find life beyond our solar system. The Von Braun is roughly the size of a nuclear attack submarine and travels at 37,000 miles per second, 20% the speed of light.
According to Einstein, there's an ultimate speed limit in the universe. Mother Nature is like a cop that says you cannot break the light barrier. Now, the nearest star is 4 light years away, and Darwin, traveling at 20% the speed of light, will take 42 years to make that journey.
The metal composite nose shield that protects the ship is cratered by collisions with space debris accumulated during the 42-year journey to Darwin 4. The planet orbits the larger sun of a binary solar system in a zone just close enough to its own star for comfort, a sweet spot astronomers call the Goldilocks zone.
Not too close and not too far away, but just at the right distance that the planet can support liquid water on its surface.
The Von Braun's first priority is to call home. A digital message will be sent through a laser beam, but the limits of time and space impose a roaming charge for long distance. Even at the speed of light, Von Braun's transmissions to Earth take 6.5 years, making it impractical for engineers to correct problems. So Von Braun and its probes will have to think on their own. The first phase of the mission is to deploy the Darwin Reconnaissance Orbiter, or DRO.
It's going to spend months monitoring weather, looking for geology, looking for signs of life.
It's going to map the entire planet, and it's going to rotate around the planet, and it's going to give us some detail on the topography.
We learned a little bit about the planet via the space-based telescopes that were around around Earth, but now that we're actually there, we're going to look down and confirm that our guesses were correct.
So that when we put these probes down, which can only explore a small fraction of the planet, we get the most out of it.
Images surge through the DRO's camera lens. Infrared, radar, and visible light pictures reveal an equatorial mountain range and vast plains swirling with weather systems. Darwin 4 has no oceans, just a small blue sea. Von Braun's computers sift through thousands of destinations before selecting the one landing site with the most to offer. The Von Braun launches a probe about the size of a dump truck named Balboa, after the famous explorer. Balboa enters Darwin's airspace as our first ambassador to a pristine alien planet. The first contact between Earth and Darwin literally falls to pieces. But the planners of the Darwin mission have prepared for just such a scenario. The Von Braun vehicle carries 2 additional probes. Probe Leonardo da Vinci is nicknamed Leo. Leo is followed by a twin probe. the Isaac Newton, a.k.a. Ike. The probes enter the atmosphere just like the space shuttles do on Earth. The final approach is a lazy S pattern to burn off excess speed before landing. Temperatures on the surface, 70 degrees Fahrenheit. Leo is first to land and emerge from his vehicle. Leo's bird-like head is crammed with sensors. Driven by protocols embedded in his software, Leo confirms that Ike's landing is on track and sends a status report to the Von Braun. The news that Leo and Ike have landed is beamed to Earth. Perhaps it's fitting that scientists who were babies when the Von Braun left Earth now announce the birth of interstellar space travel.
Watching these probes from back on Earth would be much like sitting in the back of an auditorium watching your child at a spelling bee where you know the answer and you're sitting there hoping that they're going to make the right decision and come forth with the right answer, but also knowing that you can't do a thing to help them at this moment.
Darwin 4 has a denser atmosphere than the Earth's, and the probes would have been designed to cope with that. Now, we would have known that the atmosphere was in fact denser before we got there. The way we would have known that is by looking at the spectrum of this planet and looking at the signature from oxygen in the planet. That oxygen signature would have been so broad, we would have known there was much more oxygen there in that atmosphere than we have on Earth.
Well, today, our awareness of the universe has expanded, exponentially, really. We've gotten smart. We've learned, we've done our homework. The first wave of space telescopes showed us one thing. Earth-based telescopes showed us another. Physics, computers, mathematics has come together in a beautiful confluence that has allowed us to recognize what before was unmeasurable.
Next, the probe called Da Vinci explores a puddle and discovers a micro-universe. But life forms on Darwin come in many sizes, and some of them are lethal. On Darwin 4, probes Da Vinci and Newton are backed up by a menagerie of mini-probes. Within minutes, their sensors detect a mysterious presence.
Recently, some astronomers have said, bah, humbug. The conditions for life are extremely rare. For example, you need a large moon to stabilize the orbit of the Earth, or else the Earth tumbles in its orbit. You need a large Jupiter to clean out the comets and meteors of the solar system. You have to have so many Goldilocks zones. The Earth has to be just right for this, just right for that perhaps we are alone. Well, I don't think so. Because if you look at the number of stars in the heavens, perhaps 10 billion trillion stars that are within the range of our telescopes, and you realize that half of them, perhaps half of them have solar systems around them. And if you play the odds, you come up with the realization that perhaps there are billions of planets in our universe that have conditions that are compatible with life as we know it.